PDF. Hello and welcome to the AI Safety Reading Group, session 204. Today we'll be presenting Universal Intelligence, a definition of machine intelligence by Shane Legg and Marcus Hutter. Given some feedback from participants in the reading group, I'd like to try something somewhat different from what we normally do, which is instead of summarizing each section almost chronologically, I'd like to emphasize key points and make this a rather short presentation. I'd also like to focus on a discussion at the end, and I have handwritten notes here, so the slides will be somewhat sparse. If I've covered something on a slide and I continue talking, that's because what I have written is more important than what's on the slides. It should be somewhat obvious. And I have a new photo of an owl, which is not copyright protected, I found. So that's neat. Anyway, we can go to the next slide. So this is a little bit of background about the authors of the paper. The first author on the paper who contributed most of the work is Shane Legg. He has a PhD in computer science from USI in Switzerland. This is the lab that Jürgen Schmidhuber is at. He has a bachelor's in mathematics and a master's in technically discrete mathematics and computer science. Shane started his work in machine learning at the University of, I believe, Auckland, maybe, working on the Weka project, which is a graphical user interface for these machine learning algorithms. Perhaps it's the wrong place, but he worked on the Weka project. And then he did his master's on universal induction. So he also became a co-founder of DeepMind during his time as a postdoc at University College London in the Gatsby Computational Neuroscience Unit, and he received the Singularity Institute for Artificial Intelligence Prize, which was $10,000 Canadian for his PhD work. We can go to the next slide. The next author is probably quite well known, Dr. Marcus Hutter. He's now a senior research scientist at DeepMind, but formerly he was a professor at Australian National University. He's notably known for the AI-XI model or AI-Chi-I model, depending on which version you'd like to look at. He also worked at IDSIA at USI, and he was the supervisor of Dr. Legg at this time. And we can go to the next slide. So the primary focus of this paper is the following problem, and that's what nobody really knows what intelligence is, and that's what they say in their abstract. In watching talks Hutter has given, or not Hutter, Legg has given on his work, he's described the two types of people that talk about AI research in particular. And one type is someone who works on computer vision, which we'd now probably extend to the area of machine learning or deep learning or reinforcement learning or other algorithm-based problems, whether they're classification or something else. These people generally will say, well, yeah, I'm not really working on artificial intelligence. I'm working on a narrow subset of machine learning, which creates high resolution images or classifies images or gets a car to drive. And they don't really claim to be solving intelligence. They claim to be doing a much narrower problem. But because of branding or other reasons, they just kind of say, yeah, this is artificial intelligence. It looks good. And that's becoming more and more popular now. And the other type of person that Legg has talked about is one who claims that intelligence research is going to be people who are working on creativity or compressibility or other language that's not well described. And these people he has less respect for, because the first kind of people at least know that they don't really have a clear definition. But the second kind of people claim that intelligence is too difficult to work with, which is quite interesting. So what he did in this paper here is he collected informal definitions by experts, and he tried to extract their essential features. As he mentions, going through every book that talks about a method of describing intelligence is just not feasible because there's so much other information that surrounds it, especially since this work was published in 2007. Full text search of entire books was even slower then. So we can go to the next slide. Another problem with intelligence is that it's usually defined with respect to humans, and that's what he calls anthropocentric. It's not that great if you can only define it with respect to one system. And if you guys looked at the sections that talk about intelligence, whether that be an IQ test or a G factor, Usually they're standardized via something like age. And again, we're not even getting comparison of intelligence among all humans. It's comparison of intelligence among a subset of humans. So you're really only able to make in-group comparisons. And the problem with that is that we can't compare the intelligence of vastly different systems. So he talks about systems that have completely different sensory features or different processing mechanisms. So we can go to the next slide. So if you get nothing else from this talk, please get the text in the green box. If you're colorblind, I only realized that after the fact, it's the only box on this page. Intelligence measures an agent's ability to achieve goals in a wide range of environments. I'm focusing on this because we're in the AI safety reading group, and many of us are concerned with what happens when systems become super intelligent. If you have a clear mathematical definition, maybe you could define it, but this has key implications for something like the orthogonality thesis, which says that intelligence and goals are separate. So if we all have an agreed upon definition, we can actually start working on making coherent statements together rather than just disagreeing over semantics. I was going to provide an image of like non-continuous function and ask someone what the derivative of it was at this point where it's not continuous. And then I was hoping some people would say, well, we can't find the derivative of that function because it's not defined. So if nothing else, remember intelligence measures an agent's ability to achieve goals in a wide range of environments. We can go to the next slide. Okay, so when we talk about measures, it's this equation. I'm probably butchering the name of the symbol, but it's upsilon, not epsilon, upsilon. At least that's what it is in LaTeX. Of pi is defined to be the sum over environments of 2 to the negative Kolmogorov complexity of that environment multiplied by the value of that environment following some policy pi, and pi is the agent. There's way too much mathematics in there to get it in the first pass, so we'll try to break it down. The important thing to know here is that if you want to do science, I don't know if he mentions this by the exact phrase, you need to be able to define what you're working with and hopefully be able to measure what you're working with. A lot of discoveries first require like key insights. For instance, getting superhuman chess required understanding game trees, and other discoveries require something like figuring out where the problem is and how hard it is. As a brief aside, the modern day notion of probability theory, where we can represent something as like the likelihood of an event happening, is relatively recent, only being discovered in the 1930s due to this person, Kolmogorov. I don't know his first name. And he also invented this notion of Kolmogorov complexity. So fun fact. We can go to the next slide. So we had this kind of dense mathematical equation. So let's briefly just talk about it. So an agent is something that can select actions, that can move right, move left, output some text. That's generally what he's talking about. An environment he represents by the letter mu. He defines it with respect to probability, which I just mentioned, but explaining that in a 20-minute summary is a little bit more difficult than I'd like to. If you'd like, we can discuss the specifics of it after the talk during the discussion. Now, if we go back to the text definition, intelligence needs to be across a wide range of environments. So they define the environments which as a set, and then they just define it to be the set of all computable environments. Computable is a restriction that you need if you want this to ever run. There are some philosophical implications of it, but it's usually not a problem. Goals are represented by some value. So usually how much reward you can get following some policy function. It's usually discounted in some way. It can be represented by tables or other stuff, but it's just representing rewards in this case. And then you have this complexity penalty. I didn't have time to draw out why the complexity is 2, but it has to do with binary representations. We can go to the next slide, I think. So the other key idea is that in theory, you could compare the overall intelligence of agents In practice, we can only approximate the intelligence of agents across a finite set of environments. Prior to the talk, it was mentioned that this work isn't necessarily grounded. To respond, yeah, you can't actually make this comparison. I kind of use this as almost a counterexample. You can't, with this definition, compare the intelligence of a calculator or a baby. In theory, you can, but in practice, you can't. Now, a feasible solution to this might be to compare the intelligence of a calculator at some task versus the intelligence of a baby at some task. For instance, the calculator can't burp, it can't be patted on the back because it doesn't have a way of, it doesn't have the sensory system for any of these things. I think we can go on to the next slide. The key ideas are that we have a definition and we, in practice could, or in theory could use it, but we can't in practice. One of the assumptions in the model of universal intelligence is based on this idea of a reward hypothesis. So in the beginning, we started talking about, the paper discusses human mechanisms of measuring intelligence. So we're only comparing humans within groups, specifically children. And then we want to extend it to other types of humans. So like older adults, children of various ages. Then they compared French children to American children, and different intelligence tests had to be developed to compare these different groups. But other intelligence work wanted to compare animals. And the problem that the authors introduced was that you can't tell an animal what you want it to do. You have no way of saying, hey, can you go fetch me a cup of coffee, or sit down, please stop jumping around. So what animal researchers have tried to do is coax or guide animals to doing some goal that they wanted. And usually this is done via reward. Sometimes it's sucrose, sometimes it's sex, sometimes it's neural stimulation, or sometimes it's you want to guide them by punishment. So you'll put shock wires somewhere and you'll try to get them to stop doing a behavior, continue doing a behavior based on this negative reward. Ultimately, these mechanisms for trying to get a system, in this case an animal or a machine, are based on this idea that you can get these systems to achieve a goal using some reward. Now, you can go to the next slide. The idea is that you can do any goal with a reward, but that introduces a really big problem. To achieve goals, one needs a reward signal. There's two papers by DeepMind that I don't think people are familiar with. One is Scikit-Lab, and the other one I don't have the name of. But they introduce environments where they'd like to train their algorithms, and then they like to compare them. But they quickly abandon these techniques because the reward wasn't well defined in these environments. And what happened is people said, oh, well, you're just cheating by putting reward in this environment to see how a system will behave. Like you're essentially, you're coaxing it, and that's not real intelligence. So they moved on to games where they could more easily demonstrate the universality of their algorithms. But to really illustrate what I mean by this, we can go to the next slide. The reward hypothesis kind of becomes like, I don't know if it's trivial is not the word. It's not as strong as people think it is, because if we had a good representation of rewards for goals we'd like to do, we could just specify a system to achieve that goals. I think this example looked really good. This is a game called Temple Run. I think it was popular a while ago. You can see these shiny pieces here. This agent just goes forward the whole time. There's no way to stop it. And there's hazards in the way. So you can go left, right, up. I don't think you can go down. And then you try to collect coins, and the task becomes more and more difficult over time by increasing the amount of hazards and the amount of actions you have to take. So you can clearly be super intelligent at this game if you just collect as many rewards as possible and avoid dying. But for many tasks, in particular mathematics, rewards are sparse and it's very hard to define. So I'd like to point out that limitation of this model is you'd have to frame everything in terms of rewards, and that's really difficult to do. So that's why you see very few reinforcement learning robots in the world. We can go to the next slide. I am going to use this for the discussion. I spent a long time making it. So please, somebody ask a question about it, even if you don't care later, please. Essentially, this is a comparison of tests and definitions. There was a table in the back of the paper, but that table used big dots and small dots. It's very hard to parse. So we can go to the next slide. This is just something for reference later. There was something that was mentioned. It may have been a technical detail that people skipped over if they were looking at the mathematics, but it's important to know that rewards are bounded. The reasons for this are a couple-fold. You can't, they chose this way of representing it so you could have a superintelligence. AI XI being the superintelligence, which is kind of like maximized in this model. But it's interesting that AI XI was created prior to this definition, I think. I'd have to double check, but anyway, there is a superintelligence by this model, but we don't know what the precise limit is. I show a number line here just because it's continuous values between A and B, and you can, actually continuous probably isn't the right word because we have a computable agent. But there is a way of directly comparing intelligence of these systems theoretically, meaning that you could have the baby as 0.2 and the calculator as 0.1 or vice versa, or whatever the number is. You could numerically represent the intelligence of systems. And we can go to the next slide. Okay, that is the reference to the paper. If you guys would like to see it, please let me check if I have anything else that was really important for the discussion. There's different ways in which machines can be represented. Animal tests and human tests don't necessarily compare well, but I really wanted everyone to get the key insight, which was in green, that intelligence is defined to be the ability to achieve goals in a wide range of environments. And the reason I'm presenting it here is that, again, this has implications for the orthogonality thesis and for instrumental convergence, as well as various problems in AI safety. So we can go to the next slide. So thank you guys for listening.
Thank you very much for your presentation.